Well, now we're going to create a scene which is going to be where the animation is going to be varied using a music source. So I'm going to use a particle system to demonstrate this. So first of all, let's set up an emitter for the particle system, which is just going to be a sphere. And I'm going to make the sphere into a polygon mesh because it's easier to emit particles from the inside of a polygon mesh, which is what we want to do later on. And I'm going to rename this emitter. And we want to animate it along a path, so let's create a curve object. And I'm going to just draw a path here, like so. And let's rename this path. And I want to edit the point so that it comes off the ground plane in some places, but first of all let's change it into a NURBS curve. And I'm going to hit S to select and hit 2 for points, and I'm going to select some of these points over here, like so, translate them upwards, select some points over here, translate them upwards too. Now to get the sphere to move along the path, all we need to do is look at its path object parameter and choose our path. Accept that, and we should keyframe the position values so that it moves along the path with time. Before I do that, I'm going to change the frame range to 100 frames, and I don't want to stretch the channels, so we're now 0 to 100. So the initial position is going to be 0, so I'm Alt left clicking there to keyframe that. I go to the last frame and it's going to be 1, and I go to Alt left click for that as well. So the next step is to create a particle network. Before I do that, I'm going to hide the two objects we've just created. I'm going to lay down a geometry object. I'm going to call it particles. Let's dive inside, delete the file node, and lay down an object merge. And that's going to bring in our source. So I want to transform it into this object. And our source is going to be the emitter. And then I'm going to lay down a transform SOP. We're going to use this later to vary the position of the sphere according to the music's volume. Next we're going to add on a pop network, dive inside, lay down a source, and I want to emit the points, or the particles rather, from the volume, that is the inside of the sphere. I'm going to use the first context geometry, which is our sphere, and I want to birth, to start with, around 1,000 particles per second. And I want to create a group of the particles that have just been birthed. What this does here, the birth group, is create a group and puts all of those particles that have just been born, this frame, into that group. The next thing I want to do is add some curl noise. And curl noise is a really nice way to affect your, and we can see the effect of it there already, it's a very nice way to affect your particles so that they disperse in a random fashion. But I'm going to take the frequency of this right down to say 0.3, and the amplitude up to 2, and the turbulence up to 4, let's say. And I'm going to use an advection type of update velocity, and that should give us a nice dispersion of our particles as the sphere moves around the path. The next thing I'm going to do is add a color pop, and we're going to use this to vary the color of our particles according to the pitch of the music. And finally I'm going to lay down a render pop, and I want to render our particles. I'm going to make them slightly bigger, 0.3, and I'm going to render them as disks to start with. So that's set up our scene, so we can now look at creating our CHOP network. So let's start by laying down a CHOP network to introduce some music into our scene, and I'm going to call this music. And let's dive inside. Now we can use a CHOP file node to bring in a music file. Houdini recognizes a number of different types of file. It unfortunately doesn't recognize the MP3 format, but I've converted a short extract from some music here into a .wav file, which it does recognize. So we can bring this in and visualize it, and we can see in our motion view that we have our music. And it has a lot of detail. If we zoom in here, we can see that huge amounts of detail. Even between different frames, we've got a great deal of detail. And the reason for this is that in the CHOPS context, Houdini stores an entire curve at once. It doesn't recalculate it at every frame. It stores it by storing samples and then drawing the curve around the samples. And we can in fact see those samples. Let's zoom right in. If we right click on the view and select dots, and we can see these are the samples which it's using to construct this curve. And if we middle click on our node, we can see that the sampling rate is 44,000 samples per second, which is an enormously high rate. And that's why this particular music extract is taking nearly 2 megabytes to store. And we'll want to address that in a moment. Let me return the view to its normal. And I want to try and locate the beat of the music. But first of all, let's listen to the music. And we can do that by bringing up our audio panel with the button down here. And if I select Scrub, I can choose either a CHOP or a file as the source of our music. I'm going to choose the file node that we've just laid down. And when we do that, we can see that the music's waveform appears here on the time bar. And we can also listen to it by playing through the time bar. And we can do that by selecting the real-time playback button here and then just hitting play. Like so. I enabled this time bar here, by the way, in the motion view by right-clicking and selecting time bar. Now we need to try and isolate the beat of the music, because it's the beat of the music that I want to use to drive the movement of the sphere which is emitting the particles. And I can do this by using a pass filter. Now we know that the music beat will tend to be at low frequency. So what I want to do is try to cut off frequencies above a certain level and leave only the low frequencies. And by default, this is what this pass filter is set up to do. It performs what's called a low pass, which keeps frequencies below a certain frequency, in this case 2000. You can also keep higher frequencies above a cutoff point, or you can keep frequencies between two different bands. So let's change this high cutoff to 200. We can see we get a simpler set of curves with a much clearer beat. In fact, I can lower this down probably to 150 or even 100. These are the beats that we're going to use to drive our ball's motion. But at the moment there's far too much extraneous noise here from the rest of the music to be useful for driving the ball. So I want to try and simplify these curves. And one way I can do that is using a envelope chop. And what an envelope chop does is look at the maximum of our curves within a particular range and create a new curve based on that. So let's visualize that. And as you can see, it's producing these curves like so. I want to also use this to resample the channel as it passes through, so that we eliminate quite a lot of that detail and make its memory footprint much smaller. So I'm going to click Resample Envelope, and we can see that it's now only taking a few samples to construct the curve, which has become much more blocky. That doesn't matter too much because we can smooth it out later on. What I want to do next is to lay down a trigger SOP. And what a trigger SOP does is use the value of the incoming channel to trigger an event. And each time the event is triggered, the trigger SOP produces a curve of its own. I'm going to increase the threshold. Let's visualize both of these at once, in fact. What I want to do is every time the incoming channel rises above here, let's say 0.7, I want to trigger an event. And let's now have a look at what that, let's turn off the dots and visualize our trigger node. And we can see that instead of the complicated pattern we had before, we have a fairly regular set of curves. And the reason that we've got these regular set of curves is because the trigger is replacing or is adding one of these curves every time the incoming channel reaches above a certain level. And these curves are made up, let me zoom in, of a number of different components. They are what's called an attack, sustain, decay, release envelope. And the components here are attack, this is this part. Then Houdini has a thing called the peak, which is the flat part on the top. Then there's a decay, and at a certain point that moves into a release. So we have 4 different components of our curve, and we can edit these here. For example, we could increase the attack length, and that increases the length of this part. We can increase the peak length, which increases this part on top. We can increase the decay length, which is this part here. And finally, we can increase the release length, which is this part at the bottom. And we can also change the position of this kink here, moving it up or down. Now, in fact, we can use the default values for the effect that we want to achieve. Let me home our view so that we can see everything. This is going to be reasonably good for moving our ball. So let's add a rename chop. And the reason I'm doing this is because at the moment our channel is called something not very memorable. And I want to call it height, because it's going to drive the height of our ball. And then I'm going to add a null, which is going to be where we're going to fetch the result of the chop network from. And I'm going to call this height out, like so. Before we move on, let's just have a look at how this corresponds to the music. And in fact, we can see that the peak of our envelope is happening after the beat of the music, and that's because the beat is the thing that is creating this shape. And actually that's what we want, because we want our sphere to appear to be propelled upwards by the beat. So we want the viewer to perceive the beat happening, and that providing some impulse to the ball. We can in fact increase that separation between the beat and the curve using a delay chop. And we could, for example, have a delay of 0.05, and if we can visualize these two together, we can say that all this has done is move the curve slightly to the right. So there's our output node. Now let's look at how to bring this into our geometry level. The next step is to address the color of our particles. And just as a demonstration, I'm going to see how we can use the varying pitch of the music to drive the colors. So the first thing we need to do is lay down a pitch chop. What a pitch chop does, it has two modes, but the mode we're going to use it in is the mode multiple frequencies. And what this does is to break a frequency range into a series of frequencies and then essentially do a pass filter on each. So in our case I want 3 frequencies, 3 variants of frequency, because I'm going to drive the 3 components of color. So we have one channel coming in, and we're going to have 3 channels coming out. The 3 channels representing the 3 frequencies which this has been divided into. And let's visualize this on the motion view. And we can see that we've got 3 different channels, some of them much larger than the others. And we need to address that, and I'm going to do that using a limit chop. And a limit chop is a way of confining your curves to a particular value, and I'm going to use the loop version of this, which will loop round values which exceed the value that we're putting as the range. And I want a range of 0 to 1. It's home my view. Now we can see we've got 3 curves which are more tightly integrated between 0 and 1. And at the moment we have these obscure channel names, so I'm going to again use a rename chop to rename them to red, green and blue. And then finally I'm going to add a null which will allow me to identify where I'm going to fetch my data from, and I'm going to call this color out. Now if we go back into our particle system and into our color node, we can see that we can set the color using these 3 parameters, and as before I'm going to use a chop function, and it's going to be object music color out, and then for this first component it's going to be red, and we're going to copy this. We're going to paste the copied expression in the other components, and we're going to change the names to match the other components. So we should now find that our color will be driven by the components, the pitch components of our music. And I'm also going to set up our alpha, and I'm going to give it a random value based on the ID of our particle. So that gives each particle a different random value, and I'm going to times it by 0.1 so that our particles are not terribly, or rather they're quite easy to see through. So let's have a look at what that looks like as we play our animation. There are our particles. In fact, I need to be in the particle view to see the colours. And we can see that the particle colour, the whole of the particles are changing colour at every frame, and that's not what we actually want. And the reason that's happening is because we haven't set a group to apply the colour pop to. So we need to ensure that we set the colour of the particles when they're born, and that the particles keep that colour throughout their life. And we can do that by using the birth group that we set up earlier. That means that this colour operation will only apply to particles that have just been born. So let's try that again. And now we can see that we're getting the particles with the colours that we would expect. So all that remains now is to create a camera and to render out our scene. And I'm going to not cover that step by step, but simply append a run-through of the final render.